if you can all come here, the 10 of you, and you just come to the front so that we go quickly. And well, the first one is Besat from the UPV. Your turn.
Hello, everyone. So the work that I'm going to present is the paper that is being accepted at ICHCAI 2025. It's on contamination problem in AI evaluation. Fortunately, I don't have to explain why AI evaluation is important. Jose did it for me. Thank you, Jose. Data contamination, you know better than me. It happens when there is a leakage between train and test set. This usually happens accidentally, but it can happen deliberately for different reasons. It might happen because we want to get better, show that our model performs better than what it actually does. Or sometimes we want to fix some crucial mistakes that the model makes. For example, in a medical area, the model gives a response that is wrong, and we want to fix this. So these are the reasons sometimes we want to fine-tune these models in order to get either better results because we want to fix a crucial problem, or we want to show that our model is better than what it really is. So the question is, what's the best strategy to do this fine-tuning? The question is, if we have a limited budget, how we do that? There are good reasons why we want to suppose that the budget is limited. I'm not going to explain that in these 5 minutes, but the problem that we're going to look into is whether, if we have limited budget, we spend this budget on a variety of items and put them few times, or even one time in the training set, or no, we want to choose limited numbers and add the frequency of these limited numbers of test items in the training. Here we can see an image that illustrates this. In the first scenario, we put all the items in the test set that in this case are 2, x1 and x2 in the training set. In the second scenario and the third scenario, we only pick one of the items, and we put it twice in the training set. But then the question is, if we want to pick items for training, which one we pick? Should we pick the easy one or the difficult one? And how this affects the results. So we set the contamination budget to 500, and we trained 9 models from different families. We used 4 benchmarks, 2 of them multiple choice questions and 2 of them open-ended ones. And we calculated the difficulty of the items from level 1 to 5, 5 being the most difficult. And in the table below, you can see the different scenarios and the strategies that we examined, from putting these 500 test items once only in the training set, to putting only 5 items, each one 100 times in the training set. And the results, maybe I don't have time to explain everything, but if you only look at the blue and orange bars, the blue bars show the performance of the model after fine-tuning of those items that we put in the training set, and the orange bar show the performance of the model on the items that we didn't put in the training set. As we can see, for fixing the items, meaning getting 100% accuracy, we need more repetitions, as it is expected. But it comes with the cost of losing performance on the items that are not in the training set. It means that the model loses its generalization. But if we want to get a good result on the whole data set with the frequency up to 10, the performance increases. But later, we can see a drop in the performance. In terms of difficulty, maybe the plot on the top left shows it better that easy instances need fewer repetitions, and more difficult ones need more repetition to be solved. So if we want to optimize, it's better to pick easier instances. Thank you very much.
So hi everyone, I'm Lucia Gomez from Lab Leni at the Human Tech Institute, and I'm going to present my work on multimodal depression detection in conversations with virtual humans. Sorry. So I'm going to start with a brief introduction of the problem, then the data we collected for this project, the methods to create depression detection models, and finally results and discussion. So depression is a major public health concern that affects more than 200 million people globally, and traditional diagnosis methods include interviews and self-report questionnaires, but these methods are prone to bias. However, nowadays, with the new advances, there are more and more digital tools that use AI and biomarkers to detect depression. And among the different biomarkers used in the literature, speech is a very powerful alternative because it provides information into the individual mental states. Previous works have used datasets for depression detection, but clinical data is often sensitive and not widely available, and that's why these datasets are private. And they have mainly used semi-structured interviews, where the clinician conducts the interview, but these human-driven methods have limitations such as psychological biases, and they also present challenges in replication and scalability. So that's why I decided to collect our dataset called Depressive Indicators During Casual Talks dataset, which is a fully automated AI system that simulates casual open-ended conversations to recognize depressive symptoms. We collected data from 100 participants. We used the patient health questionnaire to evaluate the depressive symptoms, and we had a balanced sample in terms of these controls and subjects with depressive symptoms and gender. And they completed 6 conversations with virtual humans. And this is the architecture we use for the virtual humans. And we have published a technical validation of the system. So very briefly, when the participant speaks, we have a silent detection module that detects when the participant stops speaking. We transcribe this into text. Then this goes to the conversational module, which has access to the previous conversation, and also each avatar has a different narrative with different, I don't know, they have a name, gender, job, a motivation, and emotion. And we use that to create a prompt to the LLM, and we use GPT-3, and I want to remark here that we conducted the experiments before ChatGPT, so that's why we use GPT-3. And with this answer, we use a text-to-speech system to create a voice for the avatar. We use lip synchronization to move the virtual human lips. And these virtual humans, they have different facial expressions according to their emotions, and they have breathing movement and eye blinking, and they have different gender and outfits. So the participants, they engage first in conversations first with 2 neutral avatars, and then with a happy, relaxed, sad, and angry avatars in a counterbalance order. And while they are having these conversations, we monitor different signals. But I'm going to briefly mention the results we got for speech. And by speech, I mean both the acoustic and the linguistic parts of speech. So again, I'm not going to go into the details, but we took each participant turn, and we concatenate everything in a single audio, and we did the same with text. We created a single text, and we used different pre-trained models to extract speech and text embeddings. I'm going to explain that. And then for the multimodal model, we applied early fusion by simply concatenating these 2 embeddings. And we use these embeddings to train extreme gradient boost models using nested cross-validation. And we train separate models for each conversation and a single model including all conversations. I'm sorry, this is not the presentation. But yeah, okay. So just the results, you can see here the top performing models, results for each of the speech, text, and multimodal model. You can see the first column is F1 score and accuracy, and the speech models outperformed the text models, so that means that the prosodic part of the communication is more informative about the depressive symptoms, but the early fusion improved performance up to 74% accuracy. And I'm presenting here the results only for the model trained on all conversations, because they got better results, and that also means that these cross-conversation interaction patterns are more informative for the task of detecting depression. And in future work, we want to increase the number of participants. We want to implement dynamic facial expressions for the virtual humans. We want also to update the text-to-speech system and the LLM, and we can do that because we use an architecture, a modular architecture, so we can update each component independently. And of course, we want to improve the depression detection models with some more complex architectures. But in summary, this work proved that we can use speech to detect depression in our system, and speech has many advantages, such as it's non-invasive, easy to collect, we can convert it to text with automatic speech recognition. So this work presents a promising approach to help clinicians to detect depressive symptoms. So here's a QR code with a video of the project where you can see the virtual humans if you want, and that will be all. Thank you.
Yo también era una presentación, ¿no? Sí. Voy pasando el resto, ¿no? Sí, vas pasando. Tienes también eso si quieres para pasar. Vale. Pero si no, le das a esta otra.
Hello, everyone. My name is Salvador, and I'm going to present how to apply artificial intelligence in the perception model of an underwater manipulation system. So, very brief, the outline of the presentation, I'm going to talk a bit about the applications of underwater robotics, the project that we are developing in our research group, and then the methodology on how to approach the problem of 2D grasping and a 3D grasping and post-estimation using artificial intelligence. Then I'm going to show some of the results of the experiments. So very briefly, the introduction. The applications of underwater robotics can be from mapping the sea bed or monitoring underwater structures such as bridges or more complex structures such as oil and gas industry structures, or even in fish farms. So the motivation is to provide safety and comfort to the divers and the operators try to prevent accidents and automatize the processes to increase the production and reduce cost. So these are some of the projects that we are working in our research lab. Is the OptiRob, the Thinking Azul, the Cooperamos, and the Artemisa. Most of these projects are based on the communications architecture and also in embedded these robots with artificial intelligence, trying to make the robot intelligent in order to make this robot to take real-time decisions and perform some specific tasks. So for the methodology, we have a control station where we can connect to a surface vehicle, and this surface vehicle will be connected to an underwater robot. So this underwater robot, using a communication architecture based on acoustic communications and visual light communications, will be able to follow some instructions or some missions that the operator will launch. So we want to embed this robot with autonomous behaviors. So as I explained before, we have the surface vehicle, the ground control station, we have the underwater robot, and the communication architecture. So we want to merge all of these components in one system. And we use artificial intelligence as a high-level controller and a low-level controller to merge all of these components. The high-level controller can be taking decisions of the mission, whether to follow one robot or follow the other robot, or deciding if the mission is on risk and abort the mission. But we can also use this as a low-level controller. What I mean with a low-level controller is that we can use artificial intelligence in order to increase the communications layer, or can also increase the localization accuracy, or in this case, use artificial intelligence to the perception model. In robotics, these markers are called Aruco markers. Is basically that if you have a well-calibrated camera and you know the size of this marker, you can know the pose and orientation of this marker with respect to the camera. So this is one traditional way of detecting the objects in underwater environments. So what we have done here is use artificial intelligence to create a data set and then train a model. So we have a camera on the gripper of the robotic arm, and we take a bunch of images, we create a data set, we label all these images, and then we train the model. We launch the model on the robot, we determine the grasping points in 2 dimensions, and then we develop the kinematic controller. The next approach will be in 3D. So we use a multi-camera system with a stereo camera, on-hand camera. Then we launch the model in the 2 cameras. We create a mask image of the object. And then with this, we are able to filter the depth image. And with this filtered point cloud, we can estimate the pose. And if that is correct, we can test it in air and in water. With this, we can determine the grasping points, develop the kinematic controller, then we tune the controller, perform the grasp, and, well, here you can see some videos. Well, there's no videos available, but the last image is, you can see 2 robots collaborating and cooperating for pipe assembly application. And in the other video, in the other image, you can see a robot grasping the pipe. Thank you.
¿Es una presentación también? ¿Esto está conectado? Creo que esto funciona así.
All right, yeah.
Thank you. Hi everyone, my name's Carlos Galindo. I'm working here at the UPV, and I'm going to show you some work we've done in the past and we're currently doing now on main content and comments extraction. So I'm going to just show you a very brief outline of what we're going to talk today. And the first question is, of course, why? Right? Because nowadays you can just go to you can search up any scraper website and you can get lots of news, you can get data sets from Kaggle, from everywhere, right? But if you actually go to a raw web page, you're not easily able to distinguish what is the main content, right? Where are the comments? What's the relevant content I need to extract from this website? Of course, if you know the website or if you have a human, on hand, you can just ask, okay, human, what's the relevant part here? And the human will easily be able to move past any extraneous objects and say, oh no, these are just related news. This is just, a call to action for a newsletter. I can just, skip that in my mind. But we need a reliable method for non-humans, aka computers, to be able to feed data to machine learning models and other algorithms. So there's three main ways we can actually see the web. As humans are just used to the pretty pictures we see on our phones and computers, but we can also represent each website as HTML code, and you can use that code to do some semantic analysis, some statistical-based analysis. But a really interesting way to represent websites is as graphs, and you'll be familiar with DOM trees as a way to interact with a website. So our approach actually takes this DOM tree and converts this into a way we can extract the main content or comments from it. In this case, I'm just going to show you the comments extraction technique, which is newer. But both are interesting, and I'll show you links to both papers at the end if you're interested in the other one. So we start with a DOM tree from our website, and you can see that on the beginning we could say, oh, we should use a specific tag for every structure we use, and we should use the footer tag and the article tag, and specific semantic tags to show meaning. But that's not the case, right? And nowadays every website is coded with divs, tables, and span elements, right? With randomly generated class names, and if you're lucky, some IDs, right? But we cannot rely on that, right? Because maybe the IDs are written in French or in Spanish or English or in Japanese, right? And unless you have a system that is able to seamlessly switch context and do so in a really efficient manner, then our technique still outperforms those. So what we're going to do is we're going to do a topological analysis of the graph, and with that we're going to add some scores to a few nodes. Right? These scores are going to be based on the number of children they have, on the depth they are on the graph, and on the amount of text they contain. And so we can, make up a score. These are just made up, but of course you would have real scores composed of these three factors. And then we're going to group these three blocks that share the exact same scores. And thus, if we're looking for comments, we can imagine that each of these nodes that have been grouped could be one of the comments that repeats its structure if there are multiple, right? Of course, this technique does not work if you have no comments or if you have just one comment. But if you go to Amazon and go to any phone, you'll see there's, tens of comments immediately visible, and you can even load hundreds more, right? And so with these blocks, we first remove the groups with fewer than a given number of members, and that's because experimentally we found that if you include these low count groups, you would end up with a huge amount of noise at the end. If you want more details on the experimentation and how we found that out, sadly I have to say you'll have to go read the paper. And after this, we can go look up the full group this set of nodes represents. So we're going to look for the parent of each of the groups and all of the nodes contained within that subtree. And so we select these new root elements, and now we take into account the full word count. So Before we were just taking into account the number of text nodes or the blocks of text we had. Now we're counting number of words. We also count how many groups overlap within each of the groups. In this case, there's no overlap, but in most cases there is. Most websites are more complicated than this. And we also take into account, again, the depth and the number of images, but that counts against the score we're going to give them. And we give scores to both of these groups, and we just pick the highest scoring one. And in the end, we obtain what we believe, of course, this doesn't always work. We'll see with the experiments, the comment section. In the experiments, we saw really high accuracy, and compared to other techniques, we have either much better accuracy, at least 10% more, much better time results, or there are some techniques that just say, okay, we're going to give this to a human, and bbc.co.uk, we're going to ask a human to solve that and then give you the results back. And if you're curious, you can even run it on your own laptop, and you can follow this QR code to see the papers and all the tools you can use. Thank you.
Hello everyone, my name is Vicente Quiles. I'm a researcher at Brain Machine Interface System Lab, and today I'm going to introduce NeuroRunner, a window into the future of rehabilitation. The development of neurotechnology is driven by the need for effective rehabilitation therapies for motor control disorders such as stroke or spinal cord injury. Therapies that can be delivered in a repetitive, controlled, and objective way, offering advantages over traditional manual rehabilitation. Therefore, we propose new approaches based on measuring the patient's active cognitive engagement in the task while making the experience attractive. So, through the brain-machine interfaces, we can register the user's brain electrical activity. We then filter that signal, removing the noise, and later we processing those signals, identifying the most relevant patterns. Later, with those signals, we make a classification of the patterns and try to separate those patterns. Later, with that model, we try to predict the intention of the user and also control the interface. So we are providing real-time feedback to the user. Originally restricted to gel-based lab setup, this technology can now be deployed in more portable and reliable solutions with less electrodes and without gel. So, why perform motor imagery? To control the interface, we are using motor imagery because it actively engages the user in mental movement tasks. While they imagine movements, we record and decode those signals to provide real-time feedback to reinforce the same neural pathways involved in the real movement. No? So we are activating the same pathways with motor imagery and with the real movement. In this way, we are promoting the neuroplasticity mechanism to improve the neural activity and consequently improve also the motor function of the patient. So, we are developing a game called NeuroRunner in which the user control the main character performing relax and motor imagery. They should perform motor imagery to complete the game. So, the game has two stages. In the first calibration state, the user follows the instructions and doesn't control the character. In this first step, we are building a neural model with the data of this first calibration state. Later, with that model, the user should control the character performing relax to stop and motor imagery to start running, no? So with the previous model, we are controlling now the character. When the enemy on the left appears, the player should perform motor imagery to start running, to avoid the enemy. And later, with the right enemy appears, the player should relax to stop and kill the enemy, and later moving on. At the end of each game, we are reporting metrics on the performance of the player to motivating the user to keep trying and continue with the rehabilitation. No? This is the point. So here, I don't know. I'm going to the presentation to see the, okay. Okay. Here, one of the games, the player is controlling with relax command and with motor imagery. This game was initially tested in 5 healthy volunteers, and later was fine-tuned to start with the patient validation. 5 patients at Hospital de Parapléjicos de Toledo test the game with so positive outcomes. She is performing motor imagery, the player is moving, the character is moving, and now is relaxing, kill the enemy, and continue moving. This game now is, we are trying to transfer this to the market. No? This is the point. So thank you for your attention, and this is all.
Well, hello, I'm Carlos Alea Torró. I'm from the Vertex lead group of Brain at the UPV campus of Alcoy, and I will talk about the adaptive multimodal architecture with intelligent agents for educational purpose optimization. This is my PhD project I'm starting with. So here we have a table of contents of what we are going to talk about. So first of all, we are talking about intelligent tutor systems that are software that use artificial intelligence in order to help a student to learn a concept, to assess, and keep a feedback loop in order to make that student more capable of learning things. So the objective of this PhD project is to convert this traditional ITS system to use artificial intelligence with multi-agent architectures that can learn in real time about the analytics of the student, automate course creation and continuous content generation, always taking into account the role of the teacher, and also taking into account the new European AI Act that will classify education as a high-risk field. So here we have the architecture. This is the main part. We have two main systems, as you can see, System 2 and System 1. This is based on DeepMind Talker Reasoner paper that talks about we have a system that we must need continuous interaction, real-time interaction with a user. So this is the System 1. And we have another part that is the System 2 that has to think and analyze all the information that we got about the conversation. So in this second system, we will get like analyze everything that is happening, take a decision, and modify what we need. So we have the learner model that it's, we have the information of the student. We follow with the learning pathway engine that will take the course materials and the concepts that has to be learned, combined with the learner model that has the concepts that the learner has already mastered, and craft the new pathway of learning for the student. We also include the adaptive learning engine that will take the information of the student to adapt to special needs. Or, for example, if you are a learner that you prefer visual thinking, visual memorizing, so the system will analyze that and adapt the content to that specific thing. This information, this content, this material is provided to the real-time system. That is the interaction, is a tutoring system and an AI that will, with different tools like function calling, analyzing what kind of things you can do. It will interact with the student in real time without stopping. And all this information will be provided to the knowledge assessment engine that will evaluate the concepts that the course must be, you must be learned in order to pass it. So it will continuously adapt the student's interaction. So this is the global view of the final system that will include also a curriculum initialization system that will craft the course. So the teacher will provide the laws, what he wants to or she wants to teach, and some extra information, and the system will start working with the structure of the course and the content generation. In a feedback loop, the teacher can give whatever thinks about it and modify in real time. So this information will be provided to the system. And also we have the guardian system that will be another module to see some learner problems that may have when trying to memorize or to learn some specific concept. So the system will adapt it in real time. So the core AI technologies that we will use is multi-agent architecture. We will use large language model and reasoning learning language model, prompting techniques, knowledge graph for concept structure and organization, and continuous adaptive learning. In the pedagogical part, we have the multimodal interaction, metacognitive prompting, continuous feedback, the importance of the teacher still in the class, as provides extra help and emotional affective that the students need, and the stealth assessment, that it's a type of evaluation during dialogues that the student didn't notice. So in the counterpart, we have the European AI Act that classifies the systems as a high risk. So there are several things that we have to take into consideration. We have to continuously monitor the risk. We have to store everything. All the decisions that the AI took has to be recorded. And if we train any model, we have to be sure that the data is fair, is not biased, that it's quite hard to do. And also we need transparency of the algorithms used, and always must be a human controlling the system. So at the end, we have a dual system intelligent tutor system that we include the teachers in this loop. So it will evaluate and assess the student and compliance with the European AI Act. And for future work, we will try to expand the multimodal interfaces, refine the algorithms, develop collaborative learning with several students working with their own, trying different methodologies like Socratic or gamifying things, and embed formative assessment cycles, like I said, the stealth assessment, but other techniques of assessment. So that's all. Thank you.
Tú tienes un PDF, ¿verdad? Sí. Ok. Como quieras.
Hello, my name is Sergio Gomez, and I'm going to present you a bit of the work of the team I work in about evaluating LLMs or conventional models. So those are the contents I'm going to explain. So let's go. I work in the Archer project that it's European funded and promotes human language technologies. This means technologies that enable machines to interpret, generate, and understand human language. This is to enhance communication between humans and the accessibility of information. So Archer means advancing robust and creative human language technologies through challenge events and research. So this basically means to bridge the gap between human speech and digital systems, making interaction with technology more seamless, natural, and accessible for everyone. So this is done through 4 annual challenges: automatic speech recognition, machine translation, name entity recognition, and document recognition. And we are mainly involved in the evaluation of the proposals of the participants. So this is how we build the evaluation pipeline. So we receive the ValgrAI systems from the participants. We run them and measure the computation time that they need. And finally, we obtain the predictions of those systems. Next, we measure the metrics of those references with the we compare our reference with the predictions from those systems and obtain the metrics. And finally, we use an automated randomized test to assess the differences between the systems and assure that they are statistically significant. This is the step in which we group them by clusters, in which a cluster is a group of systems among which the differences are not enough statistically significant. We also provide a visualization tool to watch all the results of the competition, and it shows a leaderboard, and it's interactive, so you can select the metric, some charts, and finally the possibility of downloading the data. So this is the leaderboard of our demo. We want to know who has won the competition and which is the position of each participant. And also there show the clusters that they need. Next, some charts. First, the main metric, of course, colored by the cluster of the participant. And we also show the baselines with that red dot line. Another chart shows the computation time that the system needed against the metric that it obtained. So we have that sweet spot at the left top corner. We also show the average metric, the interactively selected metric per cluster. And we also show the baseline with the red dot line. It's all the participants that are in the baseline cluster. So that is all, and thank you for your attention.
También tienes un PDF, ¿verdad? Sí. Genial. Espérate, ¿no? Ya está. Ahí tienes algo.
Hello.
my name is Anna. I'm doing my thesis in the Neurorehabilitation and Brain Research Group in the Humanities. And the project where I'm working on is about disorders of consciousness with my colleague Sandra, that is going to present right after me. So in my case, it's about the electrical and hemodynamic brain activity of these patients during motor imagery. Okay, so to start, a brief introduction about disorders of consciousness. Is a clinical condition due to a brain injury that include patients in coma, the irresponsible wakefulness syndrome, that are patients with unclear awareness and only reflexive behaviors, and the minimal conscious state that are patients that present some signs of consciousness but inconsistent responses. These patients are commonly assessed with the coma recovery scale, that is a scale that evaluates the patients depending on their responses to different stimulus. For example, if they respond to a sound like that, or maybe if they are capable to follow an object. But maybe the patients don't do these things, not because they don't understand the orders, maybe because they cannot move or they are blind. So additional methods are recommended to do to complement this coma recovery scale diagnosis. Is the case, for example, of the neuroimaging techniques that have been proposed to analyze patient responses to different stimuli, like, for example, motor imagery. You can ask the patient to imagine the movement of the hands and then measure the brain responses with, for example, for MRI. However, these conventional techniques have to be expensive and have limited accessibility for these patients specifically. So we propose the use of EEG and FNIRS that are more affordable and portable. All of you know that this is an EEG, and FNIRS, in case of do you know, it's an, you have to put over the hair and optodes. Some of them are sources that emitting lights to the head, and the others are receptors that detect the light. So depending on the quantity of light that you are receiving, you can calculate the level of oxyhemoglobin that there are in some specific areas of the brain. So in my case, my project, I aims to explore how combining EEG and FNIRS with motor imagery and artificial intelligence analysis can improve the diagnostic accuracy of DOC patients. So I'm going to tell you quickly an ongoing study. Now we have 29 healthy controls and 11 patients, and we put it a 32-channel EEG with 16 optodes of FNIRS. And the participants, as you can see, sitting in front of a screen, and they have to imagine the movement of both hands during 20 seconds and then rest during another 20 seconds. They have the instructions visually, and they have to they listen instructions too. So the EEG and FNIRS have been preprocessed with a standard pipeline, and then we apply a machine learning classification that classifies each preprocessed epochs into motor imagery or rest. For both signals, we make a feature registration. We use a linear discriminant analysis as a machine learning model, and then we evaluate the model with the accuracy. So, as a summary, for each individual, we obtain an EEG accuracy, an FNIRS accuracy, and then with combining the data of both technologies, an hybrid accuracy. You can see the results of healthy controls. The accuracies are very higher. Some of them have 100% of accuracy. So the algorithm it's capable of classify between motor imagery or rest. Then we apply this algorithm to disorders of patients, consciousness patients. The accuracies are lower, but if we analyze individually each patient, we can see that 4 patients advise significant accuracy levels. One of them, the first one, is a vegetative state patient, what means that it have very lower responses, but maybe it has covered awareness because they imagine when they have to imagine, and he rest when they have to rest. So as a conclusion, we can see that the algorithm works because of the healthy controls. We need individual analysis in DOC patients, and this individual analysis say that this method can, with artificial intelligence, can complement the coma recovery skill diagnosis. So this is.
Esto es una presentación PowerPoint.
Sí. A ver, dale a adaptar si debería averiguar. Sí.
¿Tienes algo mío luego?
No. Es como... Ay, pero... ¿Cómo se puede?
¿Le das a aquí?
Ah, vale, que se vea así. Vale. Hello everyone, I'm Sandra Goizueta. I'm doing my PhD at the Neurorehabilitation and Brain Research Group of the Human Tech Institute here at the Universitat de Valencia. Together with my colleague Ana Sierra, who just presented her research, we are working together in developing neurotechnological tools to assess consciousness in patients with severe brain injuries, in patients with disorders of consciousness specifically. So I don't need to introduce you disorders of consciousness again. I'll just say that we share the same challenge. How do we detect consciousness when patients cannot communicate through speech, through movement, not even eye blinking? So while Anna just presented an active paradigm for this purpose, where we were asking the patients to imagine they were moving their hands, this could be a very challenging task for some of these patients as it requires a lot of concentration. That's why we propose an alternative passive paradigm that requires no active participation from the patient. They just have to stay there, and we present them a set of stimuli and then analyze the brain responses to these stimuli. But how can we stimulate these patients? Our approach is based on the MAM effect. This is there is scientific evidence that these patients show stronger brain and behavioral responses when they hear their mother's voice, when they listen to a song they like, when they see someone they love, or when they hear their own name. So taking all this into consideration, we hypothesize that the brain responses of the patients in disorders of consciousness, when they are presented affective stimuli, would vary along with the level of consciousness. And if so, it could potentially complement these clinical diagnostic tools like the Coma Recovery Scale Revised, which is based only on behavioral responses. So our objective is to apply artificial intelligence to explore differences in brain responses when these patients are shown different personalized stimuli, and to use it to detect covert consciousness. So this is our methodology. We do experiments with healthy controls as well as patients with disorders of consciousness, of course, and we create immersive virtual reality videos. These videos are featuring a relative of the patient, addressing directly the patient and talking about good memories, about future plans, about positive characteristics. And also we alternate these videos with videos of strangers, of people they don't know. And of course, all these videos are normalized in terms of volume, light, position, sex of the person who is talking, and so on. This is an example of what a video would look like. And while these patients are watching these videos in the immersive virtual reality environment, we record the electrical brain activity using a 32-channel system electrocardiograph, and also the metabolic activity. So the oxygen use of the blood using functional near-infrared spectroscopy on the prefrontal area. Here you see an example. This was a patient doing an experiment. He's wearing the cap with the EEG electrodes and FNIS optodes, and also he's watching maybe his mother talking to him through the virtual reality glasses. So we've started exploring the electrical brain responses of the healthy controls and the patients. We've started with the spatial information. So after we acquired the signals and applied a standard preprocessing pipeline, we extracted the gamma frequency bands of these signals, as they are known to be related with emotional processing. And then for each subject, we extract a set of common spatial patterns. Those are spatial filters that maximize the variance between two classes, no? In this case, between to know if they were watching a familiar or a stranger. And then for every single subject, we train a different model. We train a support vector machine using these common spatial patterns to classify both responses. Now I can show you some preliminary results on this analysis. So far we've collected data from 19 healthy controls, 2 patients who had already emerged from the disorders of consciousness when the experiment took place, although they were severely impaired, and also data from 13 prolonged disorders of consciousness patients. 6 were in a minimally conscious state, and 7 of them were unresponsive. This graph shows the EEG classification's performance, so the classification accuracy of every subject's model grouped by the level of consciousness. So you see on the right, the models could correctly classify, in general, responses of healthy controls and those patients who had emerged from the disorders of consciousness. But accuracies drop when we talk about patients. Although we can see that the models of the patients in minimally conscious state had higher accuracies. This brings us to the next analysis. We also assess the correlation between the traditional clinical scales, like the Comarch Recovery Scale Revised, and the performance of our models. And we found a strong correlation of 0.71 between those 2 variables. So here, this graph, every dot represents a patient, and on the y-axis, the clinical scale, and the x-axis, the accuracy of the model. So what does this mean? It means that the model could better distinguish between the responses of the patients when they were diagnosed a higher level of consciousness. But if we look at the patients who had an acceptable classification accuracy, above chance, we see that 2 of them were the patients who had already emerged from the disorders of consciousness. 2 of them were minimally conscious state patients who, after 6 months, had emerged from the disorders of consciousness, but one of them was an unresponsive wakefulness syndrome patient who remained in the same state, and actually today he is in the same state. What does this mean? This means that there's not a perfect match between our model's performance and the clinical scales, and that both methods could be capturing different aspects of consciousness. To conclude, we built EEG-based artificial intelligence models that have the potential to assess emotional processing in patients with disorders of consciousness. And these findings might help improving consciousness assessment in clinics, and also detecting covert cognition cases. We've just started. We still expect to have a larger sample size to explore other EEG features like connectivity, to combine them, and also, of course, analyze the functional near-infrared spectroscopy signals. Thank you very much for your attention.
Hi everyone, my name is Rodrigo Barriga, and today I'm going to talk about traumatic brain injury, which is defined as a disruption in brain function or another signs of brain damage, and it's always caused by external force. Okay. Okay, it's estimated that each year around the world, this injury is being suffered by around or between 27 and 69 million people. And the consequence for the survivors are long-term and wide-ranging. They will suffer a lot of difficulties, a lot of financial difficulties in their daily life, and they also will have a higher risk of developing some neurodegenerative disease like Alzheimer or Parkinson. Okay, so as a result, they will experience less quality of life, more reliance on others, or less independence. So we aim to predict the level of functional independence that these patients will have after 1 year in a neurorehabilitation center. In this study, we, sorry. Okay, in this study, we have 2,020 patients that were not admitted in a state of post-traumatic confusional state, and all of them were 18 years old or older. Okay, we have a bunch of clinical scales. We measure motor and cognitive functions, communication abilities, behavioral ones, and we also measure the functional independence with the FIM and the Bartel index. The important point is that all of these scales, that we have all these assessments made at 3 points, at admission in the neurorehabilitation center, at 6 months, and at 12 months. And the data analysis is made by 5 different machine learning algorithms, and they all are trained incrementally because we are adding each time more variables, so the complexity increase. At first, we just have demographic data, then injury-related one, and then global neurological outcomes, and finally, the clinical status first at admission and then at 6 months. So here are the results. At 6 months, we just trained, obviously, the first 4 models. And as we can see, all the model metrics are improving. The R-square is increasing, and the RMSE is doing the opposite. We achieve some good numbers, around 70% in R-square and 10 points for both scales in RMSE. And the most important predictors are always the functional independence measures or the Bartel index in each study, in each one. And then we have some motor scales as the COPS, or etc. So for 12 months, now we could train the 5th model. That's the most complex one, the one that has more variables, more predictors. And now we achieve really great numbers, around 90% in R-square, and 6 points of error in the FIM out of a total of 1,026, and 4 points in the Bartel index out of a total score of 100. Now again, the most relevant predictors are the FIM and Bartel index, and then we have some motor functions. It could be the COPS or River-Met index, Berg scale, etc. So the conclusions that we have in this study is that the data collected in the acute stage does not have a lot of predictive power for a long-term, in a long-term way, but if we use the motor, well, if we use the assessment that is made 6 months before, our predicted value increase a lot. So These findings highlight the value of continuous assessment and support the use of machine learning tools to improve the treatment for this type of patients. Thank you very much.
Okay, thank you very much. Now we have a coffee break. You just have to go outside on the right, and outside the building you will find that we have there everything prepared. See you here at 12:20. Thank you very much.